Hello.
For now, thank you. Okay, so I guess I can only walk a certain distance. Oh, there's a more serious problem. Oh, no, there you go. Okay, all right. So a little more about the earthquake scenario. I'm not sure I can stand in the middle of the room. Oh, okay, I'll stop looking. So when we put through these scenarios together, this is another reason I like the 2003 version. They divided the faults into a series of segments, okay, and they considered scenarios on these segments. This is a technical detail that doesn't matter, except for the fact I want to show you the likelihood of specific scenarios, okay? So there's a total of 7 faults, there's a total of 18 fault segments. That means there's a total of 35 earthquake scenarios. So a rupture just on the northern Hayward fault, where we are, is one scenario. A rupture on the northern and the southern Hayward fault is a second scenario. There's a total of 35 scenarios. These are the faults in the Bay Area. So I'm going to show you some of those scenarios. First of all, a repeat of the 1906 earthquake. Okay, so that's one that ruptures the entire northern section of the San Andreas fault from San Juan Bautista up to the Mendocino Triple Junction. It's estimated that there's essentially a 5% likelihood that will occur in the next 30 years. Okay, so 5% likelihood of a repeat of the 1906 earthquake over the course of the next year. So not a huge probability. When we look at just the peninsula section of the San Andreas fault, it's about a 4% likelihood over the course of the next 30 years. And when we look at the southern section, the sort of south peninsula section, south section as it's called, it's lower. It's a 2.6% likelihood. Well, why is that? Why is it lower likelihood for that southernmost section of the San Andreas? Yeah. Loma Prieta. That's the section of the San Andreas that ruptured in Loma Prieta, so the likelihood of an event there over the next few years is reduced. Switching over to the Hayward fault, a rupture of the north and south section of the Hayward fault, which would essentially be a magnitude 7 earthquake, is an 8.5% likelihood over the course of the next 30 years. If we look at an earthquake that includes the northern section, that's us, then it's a 21% likelihood over the course of the next 30 years. Okay? So we are living right on top of one of the faults that we think is most likely to rupture over the coming years to decades. Okay, so that's the faults. That's the likelihood of rupture on a fault. So next we want to go, in order to get to the building codes, that's the end point here, is to know what building codes we need to actually understand the shaking. So we want to come up with probabilistic ground shaking. So the way we do that is we start with our predicted ground shaking for each earthquake. We then take the probability of each earthquake, and we calculate the probability that the ground shaking will exceed some threshold over the course of 30 years. Okay? And so typically people use a 50% probability of exceedance in 50 years. So this is showing the shaking intensity from intensity 1 up to intensity 10 that has a 50% likelihood of being exceeded in the next 50 years. And if I zoom into the Bay Area, you're not going to be surprised to see higher shaking intensities in these muds around the Bay Area, and then the basins, and then you can see the mountain ranges have lower shaking intensity. Okay? So just looking at these colors, if you're in parts of San Jose, the landfill parts of San Jose, we're talking about an intensity 9 or greater that has a 50% likelihood of being exceeded. Here in here in Berkeley, sort of along the edge of the hills, we're kind of down at maybe a shaking intensity 6 has a 50% likelihood of being exceeded in the next 30 years. Of course, we can say the 10% likelihood of exceedance, and as the thresholds go up, if we look at a 10% likelihood of exceedance in Berkeley, up here we're up to intensity 10. So there's a significant likelihood of very severe shaking right here in Berkeley, and this is the threshold that is used, in fact, for building codes. So building codes are supposed to be able to withstand this kind of shaking intensity. Okay, and so when we put all of those pieces together, this is what the ground shaking probabilistic hazard map looks like. The warm colors, the red and then the pinks, are the highest shaking likelihood. Not surprisingly, we see high shaking likelihood along the main primary faults, lower shaking in the Sierras, although there's these exceptions, the Garlock fault that we were talking about earlier, Walker Lane. And then, interestingly, let me just point out this section here. You can see high probabilities along the southern San Andreas and along the northern San Andreas. And this section right here in the middle, there's lower probability. That's the creeping section of the San Andreas fault. So most of the strain that is being built up by plate tectonics is being released along this section of the San Andreas fault. And so that's why that is a much lower likelihood. This is also the reason we tend to think about earthquakes in Northern California or Southern California. The likelihood that an earthquake would rupture across and through this boundary is probably quite low, though it's not impossible. Okay? So finally, just to finish up, I want to give you a sense of some scenarios for these kinds of earthquakes. So now we have probabilities for a particular earthquake scenario. We have ground shaking for that earthquake. We can now estimate the kinds of losses that we might expect in an earthquake. So now we're forecasting the losses rather than forecasting the fault ruptures or the ground shaking. So this is a repeat of the 1906 earthquake that's rupturing through this region, estimated about $50 billion in damage to buildings alone. When you put all of the losses together, that number essentially goes up by a factor of 4. So when people do these loss estimates, it's easier to estimate the damage to buildings than to anything else. And typically, there's then a factor that people apply to the building damage to get to the total losses, and it's about a factor of 4. So $50 billion for buildings, about $200 billion in overall losses. Magnitude 7 on the Hayward fault, $23 billion associated with the building, so increased that $100 billion estimated in total losses. So that's less than the losses from the repeat of the 1906. However, the probability of this event is significantly higher than the probability of a repeat of the 1906. And so in fact, this represents the highest risk. Okay? Although the loss is less, the likelihood that this earthquake will occur is greater, and so this is the highest risk when it comes to damage here in the Bay Area. Okay? Finally, we can take these numbers and we can annualize them. So we can take all of these earthquake scenarios, we know the likelihood that the earthquake is going to happen, and then the expected losses from that earthquake. We multiply them together, and we get a total loss. And we divide that by the total number of years, the recurrence interval, and we can get an average annual loss. So if you take all of the losses we expect in earthquakes, and you average them out to a fixed amount per year, this is what you get. In California, on average, $2.2 billion of losses per year due to earthquakes. Okay? So that should be good motivation to be spending some amount of money each year to try and reduce the future losses, given that we expect to have on average $2 billion of losses. That means that per capita, it's $104 per person. So every year, you will get, on average, your loss due to earthquakes will be $100. Doesn't seem like a huge number, but when you add it up for everybody, it's a significant amount. And the average loss ratio, which is the loss of the losses due to building damage compared to the total value of building, is 0.15%. That doesn't really matter. These are the numbers I want you to kind of be aware of. $2 billion losses in California as a whole, and that works out to about $100 per person in terms of losses on an annualized basis. All right, I'm going to stop there. Those of you who have any problems with the MyShake app, put your hand up. Ching-Kai will come and talk to you. Send an email to us. Please run the app for as long as you possibly can, and I'll be bringing mugs to hand out to those of you still running it in a couple of weeks.